Greetings to all the viewers. The session what we are conducting is oxidation with paracids. So here series of sessions were conducted earlier and going to be conducted in nearby days based on oxidations and reductions. In this regard, we already finished up so many oxidizing agents. So in continuation, today we entered into the concept called oxidation with paracid. Paracid denotes whenever carboxylic acid is having one of the oxygen in addition, that is the kind extra oxygen is also incorporated into the compound. Whenever this is the case, that is regarded as a paracid or peroxy acid. Alternatively, it is regarded as a peroxyacetic acid or else peracetic acid. Either of the way you can pronounce, but only the thing is, instead of CH3 C double bond OH, we can accommodate one more oxygen among, and it is having peroxy linkage in between, and it is highly reactive, being oxygen adjacent is highly repulsive in nature due to the existence of lone pair of electrons among these two oxygen atoms. That is the reason why there is the immediate liberation of nascent oxygen that causes oxidation reactions, so that the vigorous oxidations are accompanied by paracid over paracetic acid, performic acid, peroxy trifluoroacetic acid, perbenzoic acid, metachloroperbenzoic acid, and this is another kind of peroxy acid. So this is the way paracids find its own applications in the field of oxidations. So here, peracetic acid production process is also provided for your better understanding. This is the way the overview regarding this oxidation with paracid was given. Let's enter into our today's concept. Paracid oxidation is a chemical reaction. Paracid oxidation is a chemical reaction in which organic compound oxidized by paracid, which is also denoted as peroxy acid. Paracids have the general formula RCOOH. Generally, carboxylic acids are having RCOOH, but peroxy acids are having RCOOH. One more oxygen is also present along with the carboxylic acid formula. So that whatever additional oxygen is accommodated, that is responsible for the release of nascent oxygen. Where the presence of peroxy group OOH makes them a strong oxidizing agent. Here again, all peroxy acids are provided. Peracetic acid is there. Metachloroperbenzoic acid is there. Here you can find a huge molecule where you can find a large extent of peracid moieties over there. Magnesium mono monoperthalate. So let me repeat. Magnesium monoperthalate will be there. It is the kind of dicarboxylic acid, magnesium salt it will be. Bridgehead magnesium is located, and here phthalic acid, it is originated from the phthalic acid. Phthalic acid is subjected to dimerization by means of bridging with the magnesium, and paracid is incorporated among the ortho carboxylic acid moieties. This is the way magnesium monoperthalate is generated, and this is another one you can observe. OOH is a requirement for the paracid. So OOH is present upon this aromatic ring system. Instead of double bond O, you have a double bond NH. Imine group is also accommodated. So this is called a Payne's reagent. This is also having its own applications in the field of oxidation. And here also you can find trifluoroparasitic acid. Here, generally it is the paracetic acid only, but here if we replace all hydrogens with fluorine, so that what happens? Fluorines are more electronegative in nature. In order to release the nascent oxygen, the most important thing will be electron withdrawing group. Whenever electron withdrawing groups are present, release of oxygen is more feasible over there. That's the reason why metachloroperbenzoic acid is more stronger oxidizing agent in comparison to the simple perbenzoic acid. That's why metachloroperbenzoic acid finds a larger extent of applications over perbenzoic acid. That is the reason why here also in comparison to the parasitic acid, we may proceed with the trifluoroparasitic acid, being it is stronger in comparison to the parasitic acid. And here also another system you can notice, we have we have two electron withdrawing nitro groups at ortho and para position, 2,4 dinitroperbenzoic acid. This is also having greater extent of oxidation property. Here you can find is double bond OH, OOH. Though it is not the kind of carbon compound, but here the requirement for peroxy oxidation will be OOH. That OOH found in this compound called corrosive acid, right? H2SO5. So here peroxy linkage you can observe. H2SO5 is called corrosive acid, and another one is also there. This is called potassium salt. Instead, this hydrogen can be easily replaced with the potassium, so that potassium chlorate. This is a kind of salt of the same kind of peroxide only, so that you can find its own salt. This is the way peracid oxidation is. All the examples are provided for better understanding, and here you can find peroxy acids are proceeded with the degradation process in this manner, and nascent oxygen will be liberated. Common applications for these peroxy acids. If you observe epoxidation of alkenes, this is the most important application of peracid. So wherever double bond is present, that double bond, either it might be a cis kind of orientation or trans kind of orientation, both can be conveniently reacted with peracid and giving rise to epoxide formation. But the geometry of the molecule in terms of stereochemistry varied among cis and trans isomers. Whenever we are taking trans 2-butene, upon epoxidation with the peracid, there is a possibility of trans epoxy butane only. Again, these two methyl are twisted. One is inclined towards the viewer, another away from the viewer. But in case of cis isomer, cis 2-butene, if is the starting material, it can be treated with any kind of peracid and giving rise to two methyl groups inclined towards the viewer, and it is the cis isomer. And this based on this you can observe that steric retention, whatever stereochemistry there initially, that retained even after the formation of epoxide. Trans isomer giving rise to trans product, cis isomer giving rise to a cis product after the epoxidation with peracid. This is the way retention of configuration is possible by this epoxidation of alkenes by peracids. One of the most widely known application with the peracid will be alkene can be treated with peracid. Just now we observed the example over there. And epoxide formation. Epoxide is nothing but three-member ring system with the oxygen as a hetero atom is called epoxide ring. Examples are Prelusive reaction, where alkenes are converted into epoxide using parasitic acid or metachloroperbenzoic acid. Metachloroperbenzoic acid abbreviated as MCPBA. Let me repeat. MCPBA is most widely applied kind of peroxy acid for this kind of epoxidation process. So this reaction is named after Prelusive reaction. So the example is also provided for the reference. And here we can clearly observe the mechanism behind this kind of epoxidation, starting from olefins treated with peroxy acid. Whenever olefin was taken or alkene was taken, peroxy acid is trying to react with this. Being a double bond is the electron rich in nature, pi bond always having tendency to release the electrons, right? That's the reason why these pi electrons are moving towards oxygen. When these electrons are moving towards the oxygen atom, simultaneous bond bond back polarization is possible. Whenever this bond is back polarizing and the pi bond is moving towards this pi bonded electrons are pulling towards this oxygen atom, being oxygen is more electronegative. Whenever oxygen is getting the negative charge, it immediately pulls this proton. H plus will be abstracted by this O minus. Whenever hydrogen is absorbed towards this side, here the electron density increased upon oxygen. These increased electrons are moving toward this side simultaneously, that giving rise to a transition state. You can observe there is a new bond formation among the carbon and oxygen, which is indicated with this dotted line. And whatever new bond formation from the oxygen to the carbon is also denoted with the dotted line bond. Already existing bond is about to disappear, that is also represented by the dotted line bond. Whatever bonded electrons are moving, so those disappearing, that means cleavage of bond are breaking of bond is also indicated with the dotted line bond. And whatever new pi bond formation, new pi bond origination, that is also indicated with the, this is the making of bond, this bond about to form, so that is indicated over there. And already existing pi bond is polarizing towards oxygen, that also mentioned with the dotted line bond about to cleave this bond. And here is the new origination of hydrogen oxygen new bond formation. This is making of bond is indicated again with the dotted line. And there is a cleavage of oxygen hydrogen bond, and these electrons are moving towards epoxy linkage, so that oxygen hydrogen bond is also mentioned with the dotted line. In this manner, in the cyclic transition form, you can absorb 3-member transition state and 5-member transition state as well. This is the way a transition state is mentioned, right? Whenever there is a epoxide formation, we have to observe the stereochemistry of this side alkyl substitutions on alkene. Okay, so two alkyl groups, so that depends upon the bulkiness of the groups. So whatever groups are present here, that those are indicated with the wedge head bonds, which are inclined towards the weir, and whichever present towards oxygen, those are pulled away from the weir, and they are indicated with the dotted line bond. And so that we are experiencing one 3-member transition state, one 5-member transition state in this epoxide formation. Whenever this transition state is possible, so the transition state is very difficult to isolate, and it is not traced out. We are not supposed to trace it, rather it is the kind of hypothesis only. There is another possibility. R2 R3 are wedge bonds, or else, sorry, R1 R3 are wedge bonds, or else R2 and R4 also may become the wedge bonds. Second possibility you can observe in the second transition structure. So that R2 or R4 mentioned with the bridgehead, wedge bonds, and whatever R1 R3 are there, they are going beyond this transition structure, epoxide structure, where dotted line bonds are mentioned. Both the possibilities are there. That depends upon the bulkiness of alkyl groups which are surrounding this olefinic double bond. This is the way transition state is mentioned. Immediately transition state can be transformed into a product form, and releasing carboxylic acid as the byproduct. RCOOH will be removed. Whenever we are moving this bond, what happens, it will become a carbon oxygen double bond, and this is back polarized, so that pi bond is moving, OH formation is possible. Simply you can say RCOOH, carboxylic acid, is a byproduct over there. Whenever oxygen is binding at the double bond, there is a formation of this kind of epoxide. The epoxide possibility, either R1 R3 are dotted line, or else uh, R1 R3 are wedge head bonds. Both are possible. Both are here it should be mentioned as R1 R3 should be wedge, R1 R3 are dotted line bonds. Both are possible based on the bulkiness of these alkyl groups. This is the way the clear mechanism for the epoxide formation is described. there is a kind of three-membered and a five-membered transition, five-membered cyclic structure formation with the dotted lines are indicated, so that finally epoxide will be generated along with the carboxylic acid byproduct formation. And here are certain examples which are used to give the peroxide oxidation in the detailed manner. Certain examples are mentioned for better understanding. If we practice more examples related with the concept, so that it will become more familiar. That's the reason why I'm taking styrene. Any double bond over the benzene is called a styrene. This is called a vinyl benzene. Vinyl benzene, upon reacting with perbenzoic acid, treating with the chloroform. Chloroform is the solvent, being all our organic components, so that we need to dissolve in the organic solvent at 0 degree. Reaction is feasible at a lower temperature, and this is giving rise to epoxide wherever double bond is there. And we have one more question, and here also you can find double bonds, but they are unreactive towards epoxide formation. Rather, wherever double bond is there externally, that only reactive towards the epoxide formation. The reason behind this is aromaticity will not be destroyed are disturbed by means of this epoxide or peroxide oxidation. Being benzene ring is more reactive, aromatic in nature, so that we are not supposed to disturb the benzene ring. Rather, external double bond should be epoxidized. And later on, we entered into another compound where you can find a long chain, and this terminal is having parachlorobenzene, and here also parachlorobenzene is there, and here trans double bond is also located. Whenever you can find the double bond, whatever the moiety it might be, upon reaction with peracetic acid in the presence of sodium acetate and chloroform. Chloroform is treated as a solvent. Sodium acetate is taken as a catalyst, and reagent is that is peracetic acid. Whenever peracetic acid is treated, the possibility will be here the epoxide formation. This will, whatever the structure, whatever the length of the structure, our reactive site to be taken into the consideration, and the remaining structure will be unreacted. We are not supposed to disturb the entire structure. Rather, wherever a selective reaction is possible, there itself you are supposed to go for the epoxidation with the peroxy acid. And here we are taking, already epoxide is there. Where should we go for? Where should we go for further epoxidation? Because we have a double bond. One more double bond is present in the molecule, so that you may treat with this acetic acid, that is peroxyacetic acid. Here also another epoxide formation is possible. Here is the ether, here is the ester. We are not supposed to disturb them. We are not going to react with them. This peroxyacetic acid is very selective for double bond epoxidation. And here there is a competition. We have two double bonds. One of the double bond is very free. Another double bond is accompanied with the 2-methyl, so that it is somewhat sterically hindered. Though it is sterically hindered, this metachloroperbenzoic acid in the presence of chloroform solvent under reflex conditions very selective to go for this epoxidation. Epoxidation is carried at this condition only. How can we explain this reason? Though it is very free, we are supposed to go with this double bond for epoxidation, rather this very bulky one, because these two methyl groups are supposed to release the electrons by the process called hyperconjugation. Double bond density is still raised. Whenever double bond density is still increased, so that epoxidation is more familiar, more facilitated. That's the reason why metachloroperbenzoic acid will go for this epoxidation whenever methyl groups are present, being methyl are ring activating, or else we can say they are electron releasing in nature. And here we have very specific reaction will be carried. Whatever starting material geometry that will be retained, that we already discussed. Here the starting material is the olefin with the trans geometry. Whenever trans geometry is there, after the epoxidation we need to retain the trans geometry. We are not supposed to change the position of, else functional groups, metachloroperbenzoic acid, and on dissolving with the dichloromethane. Dichloromethane, what is the role of this one? It is the kind of organic solvent again, and this reaction should be carried at reflex conditions. Reflux means boiling at their boiling point values is called a reflux condition. Whenever refluxing is carried, metachloroperbenzoic acid will epoxidize this olefinic double bond, giving rise to trans epoxide again. And here is the normal alkene with R1, R2, R3, R4 substituents and supposed to be treated with per acid. This is the generalized reaction. And at the temperature of 0 to 30, normally epoxidation will be accompanied by lower temperature conditions, because when we elevate the temperature, epoxide ring will be ruptured and ring opening is a kind of consequence whenever elevated temperatures will be there. That's the reason why whenever double bond is treated with peroxy acid is also the kind of highly reactive, being repulsive forces are operated in the higher degree. That's why it nascent oxygen liberation is very common at a lower temperature only, right? That's the reason why generally epoxidation reactions are accompanied by lower temperature conditions only. And inert organic solvent might be taken. You may take acetone, you may take carbon tetrachloride, you may take dichloroacetic acid. There are two possibilities: either R1, R3 are taken back end, R2, R4 are taken front end. So epoxide, exo endo means what? Exo means epoxide is inclined towards upside. Endo means epoxide is their downward direction. This is called exo. So this peroxide may attack from the top side direction, or else it may attach to the double bond from the bottom side direction. If it is coming from the top side direction, here you can find exo. Whenever it is coming from the downward direction, you may observe the endo. So the mixture of both are possible in the equimolar ratio, that is called a racemic mixture. Whatever epoxide generated, 50% exo, 50% endo, that is the racemic mixture you can designate. This is another concern regarding the stereochemistry. And we may consider this is the benzene ring and fused with the another six member ring with a double bond, metachloroperbenzoic acid dissolving in a what is this chloroform, and reflex condition to be maintained at the 45 minutes time duration. Whenever this is the reaction condition, the provision to achieve epoxidation at this double bond rather than benzenoid double bonds, because benzenoid double bonds are not that extent reactive towards this epoxidation. And here is the reflex condition. Why? Because this double bond is deactivated by means of electron withdrawing group. Electron withdrawing group facilitate oxidation whenever electron withdrawing group is present on this paracid, but not on the olefinic bond. Olefin should be more reactive whenever electron releasing are there. That's why whenever nitro is there, we attempted reflux conditions so that epoxidation is facilitated. This is very long chain polyannular system, we can say. Multiple ring systems got fused over there, and one, two, three, four cyclic rings are available over there. Though we are having these many cyclic structures, these many ring systems, and these many double bonds, but selective epoxidation is carried only at this double bond, because these three double bonds are in aromatic ring, these three double bonds also in the aromatic entity, and these are quinonoid bonds. We are not supposed to cleave them. Only the provision is only the, because here is the conjugation, right? So this kind of quinonoid structure is in conjugation with this. Here is the double bond, single bond, double bond, single bond, double bond, single bond. This is called what? Alternative double bond system. It is not looking like a aromatic, rather it is looking like a saturated one. But we are not supposed to cleave these double bonds, because these two double bonds also in the conjugation with these double bonds. That's why they are becoming more stable. Whenever metachloroperbenzoic acid in a dichloromethane were dissolved, the selective epoxidation carried at this double bond only. You can observe the epoxidation at this double bond. And this is called what? Methoxy. This is also the methoxy. And this is called a quinonoid structure. This is the benzenoid. This is also the benzenoid. Polyannular system, it will be four cyclic rings are mentioned. Only the provision for epoxidation is this free olefinic double bond, which is which is non-aromatic in nature. So that's the reason why here is the epoxidation carried. Now we are going to discuss about the mechanism. The paracid transfers an oxygen atom to the double bond of the alkene, forming a three-membered epoxide ring. Three-membered epoxide ring will be formed. It occurs through the concerted reaction mechanism, preserving the stereochemistry of the starting alkene. Whatever alkene geometry or alkene stereochemistry is there, that will be retained. We are preserving that. Preservation is nothing but cis alkene giving cis epoxide, trans alkene is giving trans epoxide. That is called the preservation of stereochemistry. We are taking olefinic double bond, can be treated with per acid. So it is giving rise to a epoxide linkage in between. There is a epoxide linkage just like this one, right? And free release of carboxylic acid is possible as a byproduct. Here, this is the kind of application of peroxy acid oxidation to the named reaction. You can find Baeyer-Walligal oxidation. It is the most familiar kind of named oxidation reaction. In this reaction, peracid oxidizes ketone into ester, cyclic ketones into lactones. The mechanism involves the formation of Craigie intermediate followed by the migration of alkyl and aryl groups are possible. When you are taking pH, Me, C double bond O, Me. This is the starting material. Benzene is there. pH stands for phenyl. Whenever benzene is there, that will be linked with this carbon where you can find methyl. And here we have a C double bond O and here another methyl is there. Upon reacting with metachloroperbenzoic acid, what happens wherever long chain is there, that end only oxygen insertion is possible. It is the kind of insertion reaction. Metachloroperbenzoic acid used to release the nascent oxygen that is supposed to be inserted among the ketonic carbon and normal carbon atom as a ester. So normal ketones will be transformed into esters. If cyclic ketones are present, they are converted into lactones. This is a kind of ester formation is possible, and we are supposed to expect 87% of the yield by this Baeyer-Walligal oxidation of ketone into a ester form by means of peracid. The reaction proceeded with whenever we have this double bond should be migrated, and you can find O minus. That O minus and here carbon positive will be there. From this metachloroperbenzoic acid, there is a oxygen to going to be bond with the carbon, and you can find a peroxy bond with this carbon atom. So this will participate in a will participate in a kind of insertion reaction. How the insertion carried? Back polarization of electrons are possible. In here is the bond cleavage. Here entire bond got cleaved, and this able to bind with this one, and then this oxygen able to cleave the bond. Peroxy bond is very weak in nature, so that immediately cleavage fragmentation is possible, and back polarization of electrons towards this one. This is transformed into ARC double bond O minus, and here is the insertion of oxygen is possible, so that we have carbon oxygen. The filled electron lobe and these electron containing lobes of oxygen are able to form a new bond. In order to form a sigma bond, one electron from carbon, one electron from oxygen are going to be shared among the carbon and oxygen with the covalent bond formation, and these electrons are moving towards this side so that ketone retention is possible, and this ARC double bond O minus will be eliminated as a byproduct. So this is the way this PHHME, PHHME, whichever present, they retained Me wedge bond to be retained, because always in the peroxy acid epoxidation, we are supposed to retain the stereochemistry. Preservation of stereochemistry is the important criteria. That's why wedge bond should be inclined as a wedge bond only. And whatever new bond formed between carbon and oxygen is a new bond you can observe. That is the lengthening of the chain you can notice, and this yellow color lobe indicates bonding electron coming from the oxygen. Blue color lobe indicates a bonding electron coming from the carbon atom. There is a new carbon oxygen bonding you can observe, and already existing ketonic moiety is there. This is the one, CH3C double bond O. CH3C double bond O, already existing one. This is the way Baeyer-Welligal oxidation mechanism is provided. Baeyer-Welligal oxidation, wherever metachloroperbenzoic acid is there, there is a kind of proton abstraction by this ketonic moiety, so that oxonium ion formation is possible. And here we have O minus. O minus is having electron rich nucleophilicity that will abstract, that will form a bond with this electrophilic carbon of carbonylic center. And there is a new bonding between carbon and oxygen, and ultimately moving these pi electrons towards oxygen, giving OH. And that used to cleave the bond among the carbon and the alkyl. This is the most important step, we can say, that by which oxygen insertion is carried, and this entire carboxylate will be removed from the system, and there is a inserted oxygen is mentioned with the red color mark. And back polarization of electron giving rise to a ketonic one. Being proton is added from the external source, we are supposed to remove the proton from this oxygen, and that entire molecule is said to be ester. Initially, it is a ketonic one. One of the oxygen from this metachloroperbenzoic acid is coming and inserted in between ketonic carbon and alkyl. This is the way ester formation is carried in Baeyer-Welligal oxidation process. There are certain examples pertaining Baeyer-Welligal oxidation. All our specimen questions are provided. Generally, cyclohexanone, if it is the starting material, upon treating with metachloroperbenzoic acid, immediately oxygen will be released from this, and that used to enhance the expansion of the ring system is possible. Initially 6-membered ring, that will be turned into a 7-membered ring expansion reaction it will be. And that used to introduce one of the oxygen, so that lactone will be introduced. This is called caprolactam. Caprolactam is very important for the nylon fabrication in the polymer industry, so that caprolactam manufacturing is possible by Baeyer-Welligal oxidation of cyclohexanone by oxidation with the metachloroperbenzoic acid. But very peculiar examples are provided in order to understand this Baeyer-Welligal oxidation applications. When generally, if you observe cyclohexanone, there is a provision to insert the oxygen either right hand side or left hand side. But if one of the side chain is also present, so it will be the deciding factor in order to introduce the oxygen. If CF3 is the case, CF3 is called what? Trifluoromethyl. The trifluoromethyl group is present on the second carbon, and this carbon is free. So there is a provision to introduce oxygen either in between this ketonic carbon and CF3 carbon, or else ketonic carbon and CH2 carbon. There is an ambiguity in between insertion of oxygen, but selectively oxygen insertion is carried towards the free carbon atom only, rather than this kind of CF3. The reason behind this will be always within the molecule electron richness is provided, that is preferred, and whatever metachloroperbenzoic acid is coming, that releases nascent oxygen, selectively attacks at high electron density region, so that CF3 is having 3 fluoro or electron withdrawing in the maximum extent, which decrease the electron density. That's why specifically oxygen is inserting towards the other than CF3 side, so that there is an insertion carried opposite with respect to CF3. And this is the sterically accepted Baeyer-Welligal oxidation product, because electron density decreased by electron withdrawing group CF3. CF3 is having more fluoro, that's why electron density got destroyed towards the left side. So right side is only the provision to introduce. This is for what? Compound number 1. Let's go with the compound number 2. Compound number 2 is the polycyclic system, you can observe six-membered ring. You can observe another six-membered fused ring mentioned in a chair form. It is the highly stabilized one, and another bridgehead bond is also there. This is also another one, two, three, four, five, six. Six-membered ring only. Another. This is another six-membered ring only. So that it is a kind of very complicated structure, we can say. And there is a ketonic bond. In order to achieve this Bayer-Velligal oxidation, the expected product here, bridgehead carbon is there, and here bridgehead carbon is there. Both the bridgehead carbons are there. Then where is the actual provision to introduce the oxygen? Where we have to cleave the bond, where we have to introduce the oxygen? That's why we have again question mark in order to introduce the oxygen. The introduction of oxygen carried towards the right hand side again. That is because very stable molecule is formed whenever oxygen introduced at this instance. Because whenever oxygen introduced at this end, at this side, what happens here? Already we have bridged carbon atom. Bridged means already two carbons, and another extra carbon is coming from the top end. That is highly sterically hindered. Instead of electronic factors, we have to see the stereochemical factors in order to introduce the oxygen in this molecule. Steric factor matters. Okay, bridgehead carbon will render the introduction of oxygen among these two carbons. Rather, here is the free form is there, so that convenient to introduce the oxygen at this end, right side is more preferable. Go with the next one. Third one. Sorry. Third one is there where you can find ambiguity among aliphatic carbon and aromatic carbon. Here is the benzene ring. Here is the trimethyl carbon. This is the tertiary carbon. So trimethyl carbon is there, tertiary carbon is there. So among these two, where we have to introduce that oxygen which is coming by Bayer-Velligal oxidation, right? So Bayer-Velligal oxidation, oxygen preferably binds at a tertiary carbon atom rather than benzonoid carbon atom, because the stability matters for tertiary butyl rather than phenyl in comparison to phenyl. Everybody aware that if we are going to, being it is a concerted mechanism, let's suppose think the bond fission carried by homolytic manner. This is the assumption. So if we are cleaving the bond like this, just a bond cleavage by homolytic manner, so that you can achieve phenyl carbon free radical. Phenyl carbon free radical never be stable. Everybody know that, because there is no conjugation, there is no delocalization for the free radical in order to stabilize that one. Instead, you can if you are having benzyl, that is more stable. Benzyl free radical is more stable in comparison to the phenyl free radical. That's why the cleavage of the bond not yet all preferable towards the phenyl ring rather than tertiary carbon. If you are cleaving, for example, this is the molecule, right? If you are cleaving the bond between ketone and tertiary carbon is accompanied with the lone pair of electron, that is the free radical. Tertiary carbon free radical is highly stabilized due to the hyperconjugation. That is the reason why phenyl free radical is not yet all stable, because lack of conjugation. But tertiary carbon free radical is highly stable. That is because of high number of hyperconjugative structure. 9 hyperconjugative structures are possible. In that regard, there is a specific introduction of oxygen among ketone and tertiary carbon rather than ketone and phenyl carbon. That is because stability of tertiary butyl is higher in comparison to the phenyl, so that we need to insert over there. Let's go with another last molecule, that is a norbornene type of molecule. Norbornene ketone was taken, norbornenone. We can denote it as a norbornenone. It is a six-membered ring only. One of the bridgehead carbon is there. One end we have a double bond. Another carbon is indicated with the ketonic bond. Paracid is going to be operated. Whenever paracid is binding over there, there is a cleavage of bond at this instance, and whenever bond cleavage is absorbed, there is a carbocation origination. We are not supposed to go for the carbocation at the bridgehead carbocation is highly unstable. Rather, we have to introduce carbocation at this end only. And simultaneously, there is a deprotonation and a retention of ketonic group, so that oxygen is introduced among this bridgehead carbon and ketonic group only. This is the way oxygen introduction is carried instead of this side, because this bond cleavage is more feasible in comparison to this side carbon atom. So that oxygen insertion in between the bridgehead carbon and ketonic carbon, so that we inserted over here. This is the way Baeyer-Velgel oxidation molecules are provided, and their corresponding products also given with the suitable satisfied explanations. Now we go for another applications of peroxy acid oxidation. Aromatic rings can be hydroxylated using peracids, leading to the formation of hydroquinones or dihydroxy compounds. Let me take benzene, where we are having hydroxy called phenol. Phenol is having hydrogen at the other position. Everybody aware all the carbons on the aromatic ring are accompanied by the hydrogens only, right? Now we are going to treat with labeled peroxy acid. Why we are adding labeled peroxy acid? In order to understand where this oxygen and which oxygen is going to be reacted, in order to understand the mechanism in a cleared mechanism, labeling, isotopic labeling is the most important part, right? O18 was taken. So O18 isotopic oxygens were taken, and this O18 is supposed to be introduced. We are not supposed to destroy the aromaticity. Rather we are going to introduce the oxygen. This is called what? Hydroxylation, right? So this oxygen is going to be attached at the carbon atom. Whenever oxygen atom is going to be attached, that O18 oxygen is going to be attached at the aromatic carbon, and already existing OH you can notice, and labeled oxygen new joining is also you can notice, right? So whenever you are removing this hydrogen, so that benzenoid structure will be retained. Here when we are going to add this oxygen, these what we are doing, these pi electrons are going to be some extent disturbed, and here pi bond is moving this pi bond is moving towards this hydroxyl OH only, so that labeled oxygen is going to be bind with this carbon, and whatever hydrogen is there that able to bind with this carbon atom. So whenever this is the case, everything is a non-charged species only, but benzenoid structure is not there. In order to achieve the benzenoid structure, we need to go for further modification, further reaction should be achieved. In order to make that one, what we have to do, this bonded electrons are moving towards this side, H plus will be removed from this side, and whenever H plus is removed, these electrons are retained by the oxygen atom, and this moiety will be removed, and you can achieve OH over there. OH will be achieved. So hydroxy and the adjacent vicinal dihydroxy benzene will be generated. And this CH3COO minus able to accept the H plus from this end, because whenever the pi bond is originated over there, this hydrogen to be removed. So we are supposed to abstract that hydrogen and giving rise to CH3COOH. One of the labeled oxygen carried by this carboxylic acid, any other labeled oxygen is carried by this benzene moiety. That indicates what? So whatever peroxy bond we have, one of the peroxy oxygen is going to oxidize the species, and another peroxy oxygen retained by already the reagent whatever we are using. This is the labeling, isotopic labeling, in order to understand the mechanism, and by this process hydroxylation of aromatic compounds will be achieved. Now, common parasites, we are supposed to see the examples. Parasitic acid is known to you. That is CH3COOH. How many? Three oxygens are there, one hydrogen is there. And that is mentioned with the skeletal representation of electron distribution. CH3C double bond OH will be there. This is called parasitic acid. Metachloroperbenzoic acid, MCPBA. This is abbreviation. Metachloroperbenzoic acid is indicated with this Lewis electronic representation, where benzene ring will be there, and here you can find C double bond OH. Hydroxyl oxygen is accompanied by two lone pairs, and this oxygen also having two lone pairs. This oxygen is also having two lone pairs. And at meta position, meta means with respect to functional group, third is called meta. 1, 2, 3 is called meta. At third position, chloro is introduced. That is accompanied by three lone pair of electrons. Why peroxy bond is very weak? Why it able to release nascent oxygen very fastly? That is because here we have a lone pairs on oxygen, here we have a lone pairs on oxygen, which are fighting with each other. Lone pair repulsions are high, extreme. That's the reason why immediate release of oxygen is possible. That is the reason why wide range of applications we can observe for these parasites. And another example is trifluoroparasitic acid. Trifluoroparasitic acid is more reactive in comparison to normal one. That is because electron withdrawing groups will facilitate the release of nascent oxygen in the maximum extent. This is another example. And we have another example also. If simple, it is not the aromatic one, it is completely saturated cyclohexane was taken. This also going for the reaction when there is peroxy acid, metachloroperbenzoic acid is operated over cyclohexane. Traditionally treated, and solvent was taken is dichloromethane. Whenever this is the case, there is a provision to obtain cyclohexanol, means hydroxyl will be introduced. This is also the kind of hydroxylation. Hydroxyl will be introduced over cyclohexane, but the extent of product formation is infinitesimal. 5.2 percentage product is not yet all preferable, because everything will be wasted. Whatever time we are spending, whatever chemicals we are using, whatever laboratory facilities, entire process will go wasted, because 5.2 is an infinitesimal. Rather, all reactants are remained in the product only. So this type of synthesis is not yet all preferable. Let me go with alternative way. Alternative method will be chosen. That is uh, trifluoro, trimethyl, uh, methanol will be taken. Trifluoro, trimethyl, methanol. This is a tertiary alcohol. Trifluoro, trimethyl, tertiary alcohol was taken. At this condition, by changing the solvent in a conventional manner, we are having extremely low yield, and reactants remains the same. Only we are supposed to change the environment of the reaction with the solvent replacement. Whenever solvent got replaced, that used to enhance the product by 86%, and the same cyclohexanol. DFT supported kinetic study synthetic utility you noticed over there. This is the way we are supposed to modify either conditions of the reaction. Otherwise, the type of method we are opting, that is reaction pathway, to be changed. There are certain methods you can go with. Either heating is required, room temperature stirring is required, physical grinding is required, ultrasonic method you can opt, microwave irradiation is possible, or else you can go for heating, or else reflex condition. so many methods are available for in order to carry the reaction. So we need to go for the optimization of the reaction so that we can achieve the higher yield by choosing the right way. And this is the huge molecule you can absorb. Here is the benzene, here is the benzene, here is the benzene, here is the silicon, here is the amide, and very long chain you can notice. Though this much extent of complexity you can absorb, only the requirement for this metachloroperbenzoic acid is the double bond. And moreover, it's a geometry. That is only two things to be taken into the consideration. One is the geometry of the one is the existence of the double bond. Second is the geometry of the double bond. Whenever this double bond is there and moreover it is in cis form, we are supposed to go for the epoxidation in the cis form only because we need to preserve the stereochemistry. Metachloroperbenzoic acid, dichloromethane to be the solvent. RT denotes room temperature conditions are sufficient and overnight reaction is required. Reactants to be mixed up and entire night the reaction will be carried being it is the kind of low temperature reaction only and epoxide will be the product over there. And this is again a polyannular system, tetracyclic system you can observe. And here is the benzene, here is the non-benzenoid double bond. Selectively non-benzenoid double bond to be epoxidized by metachloroperbenzoic acid. We will get epoxide over there. And here is the cyclohexane. This reaction, can we name this reaction? This is a Baeyer-Welligel oxidation. Cyclohexanone to be treated with the perbenzoic acid. Chloroform is the solvent. 25 degrees room temperature to be maintained so that oxygen introduced. So caprolactam will be the product. If 5-membered ring is the case, again trifluoroacetic acid. Trifluoroacetic acid will be taken. Peracetic acid. Trifluoroacetic acid is a solvent and 10 to 15 degrees are sufficient in order to achieve the Baeyer-Welligel oxidation. And you can obtain 6-member ring system over there. 6-member turned into 7-member, 5-member turned into 6-member ring extension is observed. Whenever olefin is there, epoxidation is the product. Whenever this much of long chain you are taking with and there is no double bond, so that there is no possibility for epoxidation. But metachloroperbenzoic acid and sodium acetate, dichloroacetic acid heating conditions are provided. What we have to do? We have to go for Baeyer-Welligel oxidation so that a ketonic bond will be extended in this manner. 7-membered ring formation is possible. And another application you can observe, this is most interesting. You can, if you see, initially we have a cyclohexane. Cyclohexane metachloroperbenzoic acid hydroxylation reaction is the product. Again, you're adding excessive amount of 1 more mole of metachloroperbenzoic acid added with the same reaction conditions. Again, 1 more hydroxylation is also carried. But any carbon accommodation of 2 hydroxyl is practically impossible. That is again because of lone pair repulsions. Oxygen in the closer vicinity, not at all preferable. That's the reason why immediately it used to release the water molecule dehydration. Gem dihydroxy will be dehydrated, giving rise to a ketone. Ketone upon 1 more molecule of metachloroperbenzoic acid, this giving rise to Baeyer-Welligel oxidation for the ring expansion, giving rise to caprolactam as the product. So cyclohexane to caprolactam is proceeded with the same reagent in multiple steps. So more number of metachloroperbenzoic acid to be added. Cyclohexane initially converted into cyclohexanol and later converted into cyclohexanone, later converted into caprolactam by metachloroperbenzoic acid. This is a formic acid treated with the hydrogen peroxide so that it used to give the performic acid. Performic acid is also the kind of oxidizing agent in our topic what we are taking into the consideration today. And this is cis alkene giving rise to a cis product. Retention of geometry is most important by peroxy oxidation. Cis to be cis epoxidation, trans to be trans epoxidation. So whenever trans alkene was taken, upon epoxidation, epoxide is having one methyl front and either methyl back. Otherwise, this methyl back and this methyl front, both the possibilities are 50-50, so that recipic mixture is the product. Here we have a ketonic moiety. Trifluoroacetic acid is the oxidizing agent. Being it is a symmetrical one, either of the side you can introduce the oxygen, giving rise to a 78% of the yield. And already you're aware, cyclohexanone gives rise to a caprolactam nylon precursor. It will be by Baeyer-Welligel oxidation with the paracetic acid. And we are taking another larger molecule called isosafrole. Isosafrole is the molecule was taken. Benzene will be there. Here thioethers are there. We are not supposed to go for this kind of reaction only. This olefin is reactive towards epoxidation with performic acid. So we are obtaining epoxide over there. Again, one more molecule of performic acid is added so that it able to cleave this peroxy bond, and this epoxide is turned into hydroxy, and remaining molecule is able to attach over there and giving rise to a OC double bond called ester. Ester linkage is provided. Isosafrole monoformal glycol is obtained as a product. We are taking another example where allyl alcohol was taken. Allyl alcohol, if taken and treated with the peroxy acid, wherever double bond is there, that is epoxidized. You can mention asterisk mark over there because this carbon is optically active. Whatever star mark indicated, that carbon is optically active. And this is the kind of another application of peroxy acid for the sulfur. This is called thioether, treated with paracetic acid. Initially, one of the oxygen will be introduced called sulfone. And one more paracetic acid is added. Disulfone will be the product because sulfur is larger to accommodate these many oxygens around that. Sufficiently, the molecule disulfone, dimethyl disulfone will be generated. And here we have a four-membered ring system with the ketone, and we are supposed to go for that Baeyer-Welligel oxidation, so that ring expansion, four-membered will be turned into a five-membered. And this is not exactly four-membered actually. This is the polymeric one. N number of CH2 methylene are taken. This is the polymeric chain, polymeric cyclic ketone it will be. It will be turned into a polymeric cyclic ester called lactone, right? So in order to proceed for this kind of Baeyer-Welligel oxidation, the peracetic acid is not suitable oxidizing agent, being it is a fire catching one, hazardous in nature. Rather, we can go for long length peracid. C9 means nonene. So per-nonoic acid to be taken so that it is highly stable for safe Baeyer-Welligel oxidation process. This is the way we have to consider laboratory precautions in order to avoid fire hazards in the laboratory. And Baeyer-Welligel oxidation for the ketone to be taken, and peroxy acid, any kind of peroxy acid you may take over there, and there is a insertion of one of the oxygen in between the ketonic carbon and alkyl, giving rise to ester. Whenever cyclic ketone was taken, Baeyer-Welligel oxidation giving rise to a lactone system. And here another application found for this peroxy acid. We are taking a heterocyclic system called a pyridine. 2-chloropyridine was the starting material treated with paracetic acid. And aquated conditions also provided. It able to give the N-oxide. N-oxide formation is possible. N-oxide is also convenient to achieve because the electrons present on nitrogen are not the part of aromatic ring. They are free from the aromatic ring system because already a six-membered ring is having 6 pi electron system which retains the aromaticity. So that Nitrogen basic nature is confirmed by N-oxide formation that is achieved by this peracetic acid under aqueous conditions. And you can go for another molecule called carbon. This carbon was taken, which is called alpha beta unsaturated ketone, treated with the peracetic acid. That giving rise to a epoxide externally, because here we have a double bond that being it is a conjugated one equivalent will not disturb this conjugation, rather we can go for exocyclic epoxidation. If excess amount of peracetic acid was added, both the double bonds will go for epoxidation. This is the way you can go for. And here we have a double bond system within the ring. This is called endocyclic ring system. This ring system is able to give the geometrical isomers, being it is the kind of molecule inclined double bond whichever present will be treated with this paraformic acid, giving rise to a epoxide downward direction, epoxide upward direction. In both are possible equimolar ratio, so that racemic mixture formation is possible. This is sterically both the possibilities are equal in the manner. Whenever any alkane was taken, alkane is the kind or accompanied with the hydrogen, and trifluoroparacetic acid was taken, so that RH slowly bond cleavage you can notice with the dotted line bond, and here is the oxygen whichever present in the trifluoroacetic acid is slowly released inside an insertion in between the RH, giving rise to alcohol. This is also the kind of application we can notice. ROH is the alcohol starting from the alkane. Alkane trifluoroacetic acid reaction giving rise to alcohol as the product. And this is the one alkene metachloroperbenzoic acid when treated that able to give epoxide as the product. After the epoxide formation, here clearly notice this carbon is a chiral one. Chiral in the sense all four groups around the carbon are different. By this, we entirely completed the session. So many concepts were taken regarding this paracid oxidation. Comprehensive examples, whatever practical examples, practical feasibility of the oxidation in the laboratory, in the research purpose, everything got clearly mentioned. Hopefully, the session is very informative, and this will be helpful towards the scholars, whoever working in the synthetic organic chemistry and post-graduation level, graduation level chemistry with respect to oxidations and reductions. It is the kind of application-based concept, and hopefully this is informative for all the viewers. And the session conducted by Dr. Kavita Kottireddy Kota. Thank you very much for your patient listening. Thank you, one and all.